Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, thank you all for coming. It is my pleasure to introduce Professor Rajesh Balan from Singapore Management University. I think all of you already know him. He's a professor at Singapore Management University, and he is going to be telling us about some of his recent work on adaptive power management on displays, particularly LCDs. And he's also around for the rest of today if any of you want to talk to him. So please.
Cool, thank you. I know everyone here, actually. Hi, hello. Okay, so actually this talk is about what we presented Mobisys about last year, right, on how do we save power on LCD screens without actually impacting the user experience. I actually gave a preview of this talk about 2 years ago here, probably in the same room. Actually, I think Stefan was sitting over there, right? Yeah, so, and this time around, I actually have a full demo, etc. So we wanted to see whether this would be something that you guys would want to take up, right? Because it actually works quite well. So let's go into the problem itself. Okay, so all of you know the display is the #1 power drainer on most mobile devices. I think this hasn't changed regardless of whether you're a tablet, a phone, OLED, LCD, etc. OLED, this number is still the same. It's just that everything has come down. But the screens are getting larger, so this number is still the same. Usually numbers about 45 to 50% of your power comes from your screen, right? So any savings you make here is significant. Now, a lot of people focus on the CPU. Turns out the CPU doesn't really cost that much these days. Network, of course, but there's only so much you can do on the network. The screen, let's see what we can do. Okay, so one of the screens, and generally there are two main types of screens, right? The LCDs, which are used by everyone. There's OLED, which is used by Samsung, right? And they don't give it to anyone else. Yeah?
When you consider the entire life of the phone between charges, what is the percent that is goes to the display?
Probably more, because actually not clear, right? You actually raised a fair point. This is when it's actually being used. When it's being used, it's about 50%. I mean, over the life of the phone, it depends how often your screen's off. But if you are using it, it's going to be this or larger, depending on what else you're using. Right. Because if you're not using a network, this dominates.
Yeah, I was just wondering. Yeah. Because all the time it's got to be listening to CDMA or whatever.
But that actually turns out to be quite cheap. I mean, the GSM stuff actually is quite cheap. If you leave it on Wi-Fi, yeah, this thing will dominate. Because Wi-Fi is notoriously expensive if you're not transmitting. If you're not actually sending data. If you're just in idle state, it's actually really expensive. 3G actually is really cheap when you're in idle state. It's terribly expensive when you're sending, which is the opposite of Wi-Fi, right? So not clear. We have to do it, right? But this is where we're looking right now. I don't actually have the answer for you, right? We did it when we're actually using the phone. We're using the phone 50 or more, right? Usually, depending on what your other components are doing. Yeah?
How much GPS take up the power?
GPS, none here. This is just watching a YouTube video. GPS actually is an interesting one, right? Because it is a power hog, but most phones are smart enough not to pull it continuously. Most apps are smart enough not to do that. The only app that will kill your phone dead is Google Navigation, because that one I think turns GPS on to the max, and that one my phone will die in an hour if I turn on GPS navigation, Google Navigation. If my S2 will die in an hour, guaranteed. And it becomes hot. It really will become hot because it starts pulling GPS at 100 hertz or whatever ridiculous rate it's doing. Right? Most apps are not that stupid. Right? Accelerometer as well. If you put on the accelerometer at 100 hertz, forget about it. Right? Your phone will die in an hour, hour and a half. So sensors are not included here. Right? This is just the three main things. If you turn on your sensors, that adds a whole different ballgame, okay? Which isn't factored here at all. What else is there? Yeah, sensors. Audio we haven't looked at. Actually, nobody has looked at audio. Right? Most people leave their phone off. So I don't actually know how much the audio component also consumes. Okay, right. So so our key idea and solution, right, which I'll just cover very quickly. Then I'll actually show you a demo. I think it's more interesting to show you how it actually works in practice. Then we can go to the gory details. I always find it more interesting to show it actually works, and then we go to the gory details rather than go to the gory details and see it works because you've forgotten everything. The key idea is very simple. We play games with your eyes. right? It turns out the human visual system can easily be fooled with because what we're doing is not the same, right? Let me be very clear. The image we produce at the end is not the same. It is close enough. It's close enough that to the human visual system, it looks the same, but it's not the same. Okay, what we do is we brighten the image in careful ways, and then we dim the LCD backlight. Because what consumes power on LCD displays turns out to be the backlight. Okay, the way LCDs work, right? Quick primer for LCDs. LCDs always have a constant on backlight, then they have a filter in front, and the filter determines what color you see, right? What they do is they apply filters in front of the backlight, and then you get, if you want black, that's basically a black filter, the backlight's still on, right? So that's not very efficient, right? Which is why LCDs have better brightness than OLED, and they have no worst case performance. OLED, on the other hand, has individual pixels, right? Which have 3 diodes, each of them, and you can actually turn them on and off. Which
the same for LED displays as well?
AMO LEDs are OLED. Those are different. OLED is individual pixels. Each pixel has 3 diodes. Different in OLED and AMOLED is the kind of technology they use, from what I understand, right? And
Will an approach like this one?
no, fails miserably. OLED can't do this. OLED, there are basically only 2 approaches, which I actually have a paper on that coming up soon. But there's 2 approaches OLED. One is you change your colors, because it turns out in OLED, different colors cost different amounts of power. I think green is the cheapest on most devices. So black is the cheapest, but that's my second approach. You dim the image. You darken and you turn things black. So that's the one we are using. You know, people like Lin Zong have changed the color map. They've changed everything green. They've made everything green tinged. So you still see everything, it's just greenish. What I've done is I've turned things off. So they're quite complementary.
So could you have like a separate set of glasses that, reduce the greenness while,
Yeah, but then you have to pay the power for that. Right? So somewhere along the way, somebody pays, right? LCD is actually quite nice because you have the backlight, so you can play games. Right? You don't actually have to change the colors. You don't actually have to remove the image. So what I'm showing you here actually is 30% to 40% savings with no effect on quality, which is awesome. You get it for free.
Okay.
Yeah? You just get it for free, basically.
I can imagine it's working really well with dark backgrounds. How well is going to work with bright backgrounds?
You'll see it here, right?
It's fine.
That's why you have a game, right? It just works, right? You are actually with light background, it actually works even better because you can actually dim the backlight even more. You just have to prevent saturation of the colors, right? The key thing with light backgrounds is you have to prevent saturation. That is one of the things we work on here. Because if you brighten it too much, you saturate everything. You dim it, it still looks saturated, right? So that's the issue, right? So what we do, starting off, we use a game because a game, is 30 frames a second. Ranveer, yeah, all of research here. Okay, hello. Yeah. So we use the game. This is what the game looks like. We brighten it, and then we darken the backlight. So in the end, number 1 and number 3 is supposed to look almost similar. If you go do pixel checking, you will see they're different. But when you're actually using it, if you're not going to do microscopic examinations, no difference whatsoever, right? So let me actually show you the demo before we do the rest. I think just to show you guys what's happening. Why didn't you all come over? There's only 5.
Do you want to start the YouTube video for the people who are watching remotely?
Are there people watching remotely?
There might be.
Okay.
Unfortunately, my laptop's dead, so I can't even check if there are people watching remotely.
Okay, so let me just start a YouTube video for people watching remotely. Come on, play. What's playing this now?
The second scale is the backlight intensity of the device
Let me
itself.
start it again.
And the
Okay. Come on. Today is not working day.
Well, you're using a horrible browser there.
Yeah.
Hello, I am Karthik, and
What
in
am I
this
thinking
video
of?
I'll be
Okay.
introducing you to our system, Adaptive
Do I need
Display
the audio
Power
on?
Management, as implemented on the game Quake
Okay,
3
so-
in Desire HD. The algorithm dynamically brightens the scene and
won't get
compensates by
distracted
reducing
by
backlight
that.
intensity, thereby saving power on LCD screens while maintaining quality and brightness. Let me first introduce you to the UI on the screen right now. The first scale on the UI shows the artificial brightening of the game scene that we add. The second scale is the backlight intensity of the device itself. And the final scale shows the estimated power saved by this algorithm. This is directly dependent on the backlight intensity. Now let me show you the algorithm in action. In initially we show you the effect of just increasing the artificial brightness of the game scene.
Maybe one.
We increase this from a scale of 1 to 3. We now reduce just the backlight intensity itself so that we can see how it looks, and you can see the estimated power saved based on this backlight level. We have also performed experiments using light sensors to determine the mapping between these two metrics such that the brightness of the scene remains relatively the same. Here we show you that mapping. We have also conducted a user study to estimate the maximum threshold brightness that can be added to a scene depending on the brightness of the scene itself. Here we show you that the result of that experiments. We have determined two separate thresholds. One is called the quality threshold, which we are showing you here. In that, basically users are asked to point out the point at which the quality starts to deteriorate. The second threshold is what we call the playable threshold, which is the point at which the game stops being quite as playable. Here we show you that threshold. The playable threshold ends up saving slightly more power, but the quality loss is a little bit more noticeable. Thank you for watching.
In fact, that's the whole secret. You want to do nonlinear brightness because otherwise you would saturate like crazy. And then we compensate with the LCD backlight, right? And the bright area still looks fine, right? Now, you probably save less power, to answer your question, right? Because you can't play too many games if you're too bright. But you still save about 20-something%. And if you're willing to actually jack it up to extreme levels, right? Say you still want it to be playable, but you're okay with, you're okay with it being a little bright, right? For some definition of bright. Now, again, this is, now this is saturated. It's still quite playable though, if you actually care about your power, because now you're saving 60%, right? But this is saturated, right? Now you can actually see the effect when you take it to extreme levels, right? Everything looks there, it's there, but you don't see the contrast difference between bright and light. Right? This is the issue, how do you actually get it so that the contrast levels are correct and save as much as you can? Turns out you can get about 28 to 35 to 40% on most scenes, right? And we intentionally chose a game because this is probably the hardest thing to do because it's completely dynamic. The person's moving all over the place, right? So this is just the controls. This is not doing anything. The game's actually running fully here, right? Everything's actually on Android. This is just our backend interface to toggle the settings.
Is running here.
Everything's running here. Everything's local. This is just.
How much energy does the algorithm itself take?
Not very high. As you'll see, what we do is actually quite simple. That's the whole part, right? Because if you actually waste a lot of time. Yeah. There. This is playable. As you see, this looks quite playable actually, right? And if I didn't tell you this was modified, you probably wouldn't know.
So outside the context of a game, how would that look like? Let's say I'm browsing or I'm reading emails.
This actually works even better because that one, there's no dynamic change. You don't have any content change, so your power savings for that is actually constant. We haven't implemented it because we looked at it and went, yeah, that's really simple. Because there's no dynamic manipulation when you're in a game, right? When you're in a browser, etc., everything looks the same. It's actually quite easy. You will save about 35%. Now,
So you get maximum or a lot of power saving when the screen is kind of dark?
yeah. When your screen is, actually no, when your backlight is high, we get the most savings. When your brightness is high, we actually get the most savings. Your brightness already low, there's not much we can dim it even further. So it turns out the other way. If you're already one of those people who sets your brightness to the lowest level, yeah, we probably can't save more than that unless we turn it off. But if you're one of those who, leaves it on, or whatever the default is, yeah, we can help you. Right? It's like one of those Kung Fu shows, right? We can help you. So
all the optimizations in your case would apply directly to video as well?
everything. We are applying directly to the frame buffer in this case. I mean, this is basically a video. It's running at 30 frames per second.
Yeah.
Right?
If I'm watching YouTube video, you could be applying the same optimization.
No problems whatsoever. I mean, that's why you picked a game. Because games are usually 30 frames per second, and they have real-time constraints.
So would you benefit if you could modify the content That is the video.
Oh yeah, sure, definitely. If we could modify the content, you could make it better. But the whole point is this doesn't need to do that. This is completely content, it's completely application independent, right? It just runs fully on the laptop. Or we also have it running a laptop, which I can show you if you care, right? That's the laptop version. So this is actually Quake 3, the Android version. We actually have Quake 3, the laptop version. They implemented slightly differently because Android is a subset of Linux, so we have the Linux version. We actually did it on a giant 42-inch LCD TV for a demo I did 2 weeks ago. So it also runs on TVs, right? So we showed it to a telco, and they're like, yeah, we can put it in set-top boxes because most TVs are LCD now. No, OLED is coming, but it's not there yet, right? The video is actually on the phone, right? So you can make the content darker, so you could brighten it. The thing this will not work very well on is bright content, because then you're quickly at the saturation point, right? Because if you took something that's very highly white, like this screen, there's not much more you can brighten it, this light, because it will saturate. And that's what you saw in the second demo, right? Everything got raised so high, it's saturated. It all looked like one color at the end, right? You had no contrast. Whereas something like this, easy, right? Because you still have a lot of layers you could go up the scale to make the back is even easier, the black TV is even easier, right? Okay.
So Rajesh,
yeah.
It's hard. It looks very similar to my eye, but what about my unconscious? I find that when I play Quake 3, I eventually get queasy. Do people get queasy sooner?
They don't get queasy any sooner, any faster than previously. I mean, if they get queasy, this won't help. If they don't get queasy, this doesn't hurt.
So at the same time.
Yeah, we did a user study. We did a user study with a lot of people. So in the Mobius paper, we did it with 60 people, and they all said, yeah, perfectly fine. We ran it on the laptop, actually. Because the problem with this tablet is it's incredibly hard to play because tablet controls suck. So we actually did our user study on the laptop with mouse, keyboard, everything, and they said, yeah, it looked the same. Playable, just the same. We had gamers, non-gamers, everybody. Right? They couldn't tell the difference, which is great. We didn't tell them what was what. We just let them run 2 versions, and they said, yeah, feels exactly the same. So
how do you measure the amount of power saving?
No, all measured using external voltmeter. We do not trust software. This was the paper that convinced me all the software power savers are all crap. Software power measurers. This one is calibrated based on our previous results, right? So we know what the settings actually give us now. So it's all calibrated based on the previous results. Now, of course, it's not 100% accurate. Yeah, but it's all based on our previous measurements. So we took every possible value of brightness, gamma correction.
The pixels and the brightness.
Yeah. So we measured all of that previously. So this thing just goes with our previous measurements, right, for the same device.
Displays have different power characteristics, right? LED, OLED, LCD.
Yeah.
I don't know the the Retina screen. What's the impact of that?
Retinas is LCD, IPS.
No, but is it the power is the same? Because OLED and AMOLED is totally different. With we did AMOLED numbers, it's different.
Yeah, but AMOLED and OLED basically have the same, cannot use this because they have no backlight. So for OLED and AMOLED, you basically have to do either, as I mentioned to him, you either change the colors themselves or you darken the image, right? You turn off the pixels. Whereas with IPS, you still have a backlight. Now, how much does that save you? Not clear. You have to calibrate for the device, but it will save you quite a bit because on the LCD type things, the backlight is on, no matter what you do. So what we are doing what we are saving is actually the backlight power. We're actually dimming the backlight, right? So we trade off CPU to brighten the image. And the cool thing is, and this is why if the product guys were here, they might be able to help me out as well. In almost all graphic stacks, the last part already does an image manipulation. That is where we'll put our stuff. So it may not actually be that expensive if you're actually in a real graphics pipeline. Because all we're doing is we're applying a gamma correction function, which to the last rendering buffer, which already happens anyway in most graphics pipelines. So if you do it the right way, it should not be that expensive, right? Now, theoretically, of course, it should not be that expensive, right? But again, we'll see what it is, right? But even with our implementation in software, we are still getting these numbers, right? We'll get a little bit more. Now, this I already explained how LCDs cover, right? So just to give you a bit of background, the things we tried. Firstly, if naively dim the display doesn't work because you'll see flicker, right? We've tried this. If you just naively dim the display based on what you see, you get a lot of flicker, right? The human eye is very good at picking up flicker, right? I think it's one of those early reactions. We like seeing things out of sync. We can detect when something flickers very easily, right? So it cannot flicker, right? This doesn't flicker, right? You can compensate with increased brightness. You can linearly apply. You can apply a linear function. Problem is the bright areas get saturated, like this. So what happens is you don't see the difference between the edge and the inside. It just looks like uniformly white because everything has reached 255 level brightness and everything just becomes the same, right? So what we actually do is we use nonlinear brightness functions, something called gamma in this case. But there's lots of nonlinear gamma brightness functions. We just use gamma. It seems to work. There are other ways you can do this as well. Now, what gamma does is it basically applies a curve. It brightens the bright areas less. It brightens the dark areas more. Right? Now, what happens is you lose contrast, but it doesn't saturate. That is why the image is not the same. And I'll show you later with a histogram. You will see it's definitely not the same. Right? So this is what happens. We have the game. We brighten it. Looks kind of bright. Right? If you actually pay attention, the contrast has changed. The contrast up here has changed a little bit, if you actually pay careful attention to. But the key thing is it's not so bad that you notice it, unless you raise it to extreme levels, like what we did in one of our demos.
Can I ask you a question?
Yeah?
So I don't play a lot of games, so
yeah.
This probably is very naive. So that was the original. On the left here is the original, on the right is after you apply the gamma.
Yeah.
Why does the original look better than that?
Because the original has got more contrast. That one is too bright. You're looking at it and going, it's too bright, and some of the contrast is lost. The difference between the bright areas and the dark areas is not as wide as it used to be.
So for most people, they would agree that the stuff on the left looks better than the stuff.
Obviously,
It's not just plugged in.
definitely. If you don't compensate, the key thing is we haven't compensated yet, right? We haven't compensated. If we just gave them the thing on the right.
Okay, I'm not asking a question about your talk. I'm asking a question about two pictures that you happen to put on the screen right now.
Yeah.
So
one on the left and one on the right.
Stefan, you also have to remember that it's not just what the user wants, it's also what the game developer wants, right? There's certain semantics in a game where I want certain regions of the scene to be dark, where I might have an enemy hiding. If I go change the brightness, right, then the user can go see that enemy that's hiding over there, right? That changes the semantics of the game.
I see.
Okay.
Yeah, we're trying not to change anything like what Sharat said, and let me show you what happens. So this is the original histogram. This is your standard brightness versus pixel histogram, right? So it looks like this. All you need to do is look at the curves. Original image, compensated image. This is after gamma equals 2. And this is after we actually reduce the backlight. We do our backlight reduction. Now, let me put them together, right? Looks reasonably similar, the curves, but they're not identical. This is the key thing. We're not giving you identical images. That's almost impossible. But we're giving you something that is, for most people, is almost, you can't tell the difference, especially when these things are going by, right? So this is what you asked, right? Stefan, the middle image you can see is clearly different.
No, that's not what I asked. But
Yeah.
I understand. I asked a different question. But your point is well taken.
Yeah. So this is what we're doing. So it's not the same, right? It's close enough. So we are fooling the visual system, right? Now, let me give you some results, right? I already showed you. We actually tested an RPG game as well, just for fun, right? So there are basically 3 challenges to do this, right? Which is, one is understanding how backlight, et cetera, gamma, et cetera, affect your power savings in the same way OLED and AMOLED. We have to understand it for LCDs. We have to understand human thresholds. This is very important. You can't just naively apply this. You have to know what humans actually can accept, right? Where's the level beyond which bad things happen, right? Where can you draw the line? Very important. And finally, how do you dynamically apply it? Turned out this was the easiest part, right? Once you know all the part, applying the solution turns out to be really simple. You look at the loop and you go, yeah, every system has this, okay? So first things first, we looked at how you can save power with backlight. Turns out on many devices, we tested on two phones and 1 laptop, probably other devices as well. It turns out to be fairly linear. Now, the percentage actually changes a bit, as Ranveer said. It's not that much. Like on the HTC Hero, it saves a lot more than the HTC Magic, right? But the line is linear, right? The more power you apply to the backlight, the more power consumed by the display. Turned out this was linear, and we measured this using an external voltage meter, okay? There is some fuzziness when you go up to some values, but by and large, it's linear, which made us very happy, right? Now, how do you actually handle gamma? Turns out gamma is a very, very tricky function. Because it is nonlinear, The gamma value actually goes from 0 to 10, but if you apply 10, you will see nothing but white. Turns out the useful range is actually between 0 to 2. That's it, right? Because it goes this way. It quickly saturates at around this point, right? Because it is nonlinear. The less you apply of it, the more effect you get. Once you reach past a certain point, you've already applied too much. Applying more doesn't help. Okay, so it is. This actually made us very worried because this told us that we needed to calibrate with the humans, right? Because every setting, the difference between a 1.1 and a 1.2 was very, very big, right? It wasn't linear, so you couldn't just naively apply it. Okay, so what we did. Yeah.
So, difference by difference you mean that the y.
This is what we did was we applied a gamma value of 0.5, and this is the backlight level that will give us the same brightness for the original image. We started with the image at 255. We applied gamma. This is the backlight level we set to get the same brightness. It turned out that you needed to go lower and lower very fast as you applied a little bit more gamma because it was brightening it a lot more. And once you reach a certain point, it just saturated. As in, you couldn't get lower than that. The image was just completely wiped out, right? And it saturated really fast. I mean, this range is really fast here, this curve. It drops really, really fast. So which is why you look at those levels here, the gamma is like 0.64, 0.65, right? The levels are very low, okay? Now, what we needed to do is we needed to map that gamma to what users actually can see, right? What they actually thought was useful. So this is actually a big hole in our evaluation right now. Our user thresholds are actually generated only from 5 people, 5 grad students. We got them in because this actually needed proper calibration. We brought them in with proper light sensors, everything. Took about half an hour per person, right? Possibly an hour. We gave them a whole bunch of images of different brightness levels, compensated and asked them, does the brightness look the same to you? Does it look the same to you? Does it look the same to you? And we actually calibrated all what they thought was equal brightness with proper light sensors, etc. Right? So we brought in a proper light meter. Now this calibration is where this thing, by and large, will break down. Right? If our calibration doesn't work, if we didn't find the representative users, it means what we show you, Stefan won't like it, Sharat won't like it, I won't like it, right? Because we are not the same as these people. So if this is actually deployed, this step might have to be relooked. One criticism is these are all students. They all have reasonably good eyesight. What happens if you go with people? Well, they're all young at least, right? Their eye systems are at least reasonably young, right? So what happens if you go with more elderly people? What happens if you go with people who are colorblind? We don't know. Frankly, we don't know.
Did you see much variance amongst these users?
These students, no, because they're all about the same.
Do you have any reason to believe that
I can't answer that. Honestly, I can't answer that because we don't know. It could be the case that some people perceive brightness quite differently. I suspect that is true.
Oh,
I'm sure that's true.
Individuals that are very sensitive at these things.
I'm sure that's true. If you have individuals who perceive brightness quite differently, or people are colorblind, what we're doing it's not clear whether it will look the same. It might look the same as in the original thing already sucked. The next one might suck just as much, or it could be quite different. That one we don't know. Right? What I'm saying is I don't know whether our modification will make it worse or make it better. Right? Because, yeah?
You could imagine having a calibration step much like you do on your phone.
Yeah, set brightness level, right.
So, but you kept talking about, but we had a light meter, Will it not work if I don't have a light meter?
No, it will not work. It will actually work well without light meter. We're just being really careful. For this, we are being really careful. I suspect if you actually deploy something like what Xbox does, or something in our game, set the brightness until this thing is barely visible, will work just as well. Since we already know what goes on the back end. Right? So since we already know what goes on the back end, we can probably calibrate it by saying, please set the brightness at some level, and then we know all the other points. Right? Yeah. So this is what we got. We ended up with 2 different thresholds. Right? Conservative is what we showed you. It's playable, as in there's no difference in quality. This is the point where they said quality does not change. Right? So these are the gamma values. Notice everything is below 2, more or less. Right? So very, very low amounts of gamma being applied for different image brightness. This is where they said, yeah, it looks bad, but it's still playable. That was the second level I showed you. Right? Looks bad, but still playable. It's not the case where I look at this, I can't see things that I need to see. It looks a bit washed out, but it's still quite playable. If there's enemies there, I can still play. If there's things there, I can still shoot, right? Okay? So those are the 2 levels. That's how we calibrated it. Now, the actual algorithm itself is quite simple. It's a standard feedback loop. We calculate the average brightness of the last X samples. X is tunable. In this game, I think it is 200 samples. right? Because it doesn't do it more than once every 2-3 seconds, because otherwise you might see flicker, right? We do it on the whole image.
So X samples means X images.
Yeah.
X frames.
X frames. 200 frames. We look at 200 frames, right? Average brightness of 200 frames. Then we calculate, if it's more than X samples, we calculate what the average brightness was and apply a compensation. Or not, we leave it as it is, and then we sleep for Y milliseconds. I think right now we're doing it every 200 milliseconds. I think the Android is 400 milliseconds, right? So it's once every half second, roughly, maybe 500 milliseconds, right? If you do it too often, your CPU load goes up, and you also tend to get flicker, right? So this is something that has to work, and we have something that works. So, okay. What we did to test it is we tested on a phone and a laptop, and we gave it to users, and we also measured the power, right? So what we did is, this is an unmodified level. We gave with nothing modified, obviously. We gave with 2 levels. One is full quality, one is playable, right? So those are our 2 thresholds, right? The thing where we claim there's no difference, and the one where we claim there is a difference, but it's still usable, right? Even though it saves a lot of power. So these are the numbers we got. By default, you save nothing. When you actually turn on the power savings, you get 49%. We get less on the tablet, because the tablet actually does things a little differently, right? On the LCD, on the laptop, we actually got more power savings, because the laptop, the display is larger, right? It turns out the larger the display, the better this is, right? Kind of makes sense, because the CPU, everything is about the same in some level, right? And aggressive, we got about 70%. So on a TV, we actually do really well when we actually did it on a 42-inch TV, right? We didn't measure the power, but I bet you will do quite well. Yeah. So that part is easy. Then we actually gave it to users, right? And we said, here, let's play games. Turns out lots of people want to play games, so we got overwhelming response for this. We had 60 people. We managed to get them all in and out in 2 days. We asked them to play 3 versions. One normal, one with our system in fully playable, no difference, and one with the system set to the high setting where it's saturated but still playable. And we didn't tell them which was which. Okay? They all got calibrated by playing the game a little while first. So they knew how to play the game. They saw what it looked like by default. The key thing to take away is that the default and the very playable version are within the noise, right? They turn out to be exactly the same, right? There's no difference between the 2. We did a t-test. They're statistically insignificant, the difference. It's just artificial. This aesthetically is significant. The difference, obviously, when they saw the bad version, they said, yeah, this kind of sucks. It didn't suck that much, but they did say, yeah, it kind of sucks. Okay? It was below neutral. But these 2 were almost exactly the same. They couldn't tell the difference. In fact, that's what we wanted to see, right? We didn't tell them. They looked at it and went, yeah, to us, they look the same. Okay, the standard deviation, everything is about the same, right? T-test showed they're statistically insignificant. In terms of power, right? So this is the big takeaway. In terms of power, the difference between aggressive and conservative is very significant. Difference between, say, a 30% savings and 69% savings, huge, right? Obviously, you want to go aggressive, but it kind of sucks. But as far as the users are concerned, they kind of hated it. So these are maybe 2 settings you could set in practice, right? If you want to go extreme, right? Or maybe you don't even give it. What's really interesting is this difference between conservative and default. Basically, you get all of this for free. This gap between 0 to whatever this number is basically for free, as far as you could tell. Because as far as the users were concerned, they couldn't tell any difference, right? We had 60 users, right? We had gamers, non-gamers, everybody. And averaged out the t-test, no difference, right? And they didn't configure it. This was configured by people. The people who configured it didn't play the game, by the way, right? The people from whom the settings were taken from were not our user study participants. These were 60 undergrads. The people who did the calibration were all grad students. Okay, so that's basically the big takeaway, right? That somehow we have a system that seems to give you about 25 to 35%, maybe 40%, almost for free. It's not the same image, right? We have to be quite clear, but it seems to fool people enough that it actually works. Yeah?
So before you go into the other technologies, so when you presented the algorithm, you said that you're doing this every 200 milliseconds.
500, every half second.
Why don't you do it for every frame? That's the part I don't
It's very computationally expensive. We could, because So Stefan, you're actually correct. We could if we had a smarter way of doing it. If we are in the kernel, we could probably do it every frame if we are in the right place. We are doing it in software right now, as in we are in user space. So we don't want to do the context switch right? Because right now the way we're doing it is quite expensive. So if we actually did it in the kernel, we could do it every frame and probably even do better, right? But we haven't investigated this because we haven't gone into the frame buffer or the low-level bits of Android to actually do this.
Just to understand, so if you were to do it, let's say, every other frame, does it mean you are missing on half the potential of energy saving? Or not?
Yeah, possibly. It's an interesting question. It depends how often your brightness changes between frames. Frames are very small though, because these are 30 frames per second. Your brightness usually doesn't change that quickly, right? Because it's all user-driven. The user has to move, and users don't move that quickly, right? So we didn't see any real need to do it every frame. Plus, it was very expensive. In a real implementation, we possibly could, but again, I don't think you'll gain that much because the brightness really doesn't change that fast.
I wouldn't think changing the frequency would affect the average power at all because half the time you're not changing soon enough from a level that you would save more power, and half the time you're not going fast. All that checking more often will do is you'll have higher dynamism. Those users who can notice.
You possibly flicker, right? Exactly. I think that's also true. You might actually introduce flicker if you change too quickly as well. So it's an interesting question. Don't know the answer. This will require more in-kernel implementation where you can actually overcome the overheads.
In software, maybe you could do it faster if you just sample instead of checking the average brightness of all the pixels. If you just pick 20 random pixels and average. I mean, if you pick them all over the place, it's probably going to be a problem.
I think actually the tablet does that now because Android is kind of slow. The laptop we actually do more because the laptop has a better CPU. The Linux gives you more bits. I think on the Android implementation we do subsample, right? I think that on the Android it's actually every 2-3 seconds because this thing will show you if you do 500 milliseconds. It will get jerky, right? It will start getting quite jerky if you do it every 500 milliseconds. Yeah. So yeah, there's some holes in the way we implement it. This was proof of concept. Yeah. No, but I don't know the answer. That's a good question, sir. Right. So OLED displays I'm actually working on right now. So we actually are working on what you can do when you dim the display in strange ways. So I actually have a solution in the Android kernel a user study is happening in 12 hours back home. My minions are working on it. Yeah, for Mobisys, right? So we actually have something in the kernel that works on all applications and games. Dynamically darkens the image, right? The idea is that for most apps, the top part is the most important portion. The bottom part tends to be history, older parts. So if you could dynamically darken it in a way that, Facebook, most of the bottom parts is older content and it's infinitely scrolling. So if you're willing to change your user experience a little bit, on OLED you have to. There is no way to do it without changing your user experience as far as I can tell because each pixel is individually lighted. Right, so if you're willing to change your user experience a little bit, you can save, numbers are getting a 40, 60% power savings if you're willing to change your user experience a little bit. We don't know if they will, so we'll do the user study today. See if they will, right? But numbers are getting are quite cool, 45% with a very naive approach. Yeah?
Just comparing OLED and LCD, what's the power sort of characteristics?
It's very hard to say that. So on average, right? I've looked at so many papers. Lin is probably the expert on this. Ranveer might be doing stuff now on this. You can say OLED is on average about 40% less expensive than LCD, but its worst case is higher. If all you see is a white image, OLED consumes more power than LCD. Because LCD is constant power, not affected by image at all. OLED is really affected by image. If your background is black, you probably are at 70. If your background is mostly black, it's probably 60 to 80% the power of LCD. If your image is bright, white, it's about 20 to 30, maybe 40% more than LCD. On average, about 40% less. So OLED has this huge variation, which is why it surprises me that your Windows Phone, by default, everything's white background.
We're using
7.5.
We're using LCD.
Yeah. No, but
all the phones in the market today are using LCD.
Yeah, convince Samsung to put an OLED version.
Samsung uses OLED.
Right. Yeah. I guess the Samsung Windows Phone 8 is.
Yeah.
And by default, we have this black for email. Right? For email, right. Close to the black background.
Yeah. But most of it previously was white, which is fine on LCDs, but it sucks on OLED. Yeah. And actually, OLED is an interesting question because he asked me, is OLED common? And the answer is Yes and no. It's yes on every Samsung device. It's no on everywhere else because Samsung owns the patents. They refuse to share, right? But they have the most popular phone on the market now, the S3, I think, and the S3 and the Note, I think, dominate the smartphone. They've took over iPhones, right? So we'll see. It's not clear where the war is going to go, right? Because Samsung owns all the patents on OLED and AMOLED. So that's why Sony doesn't. Sony was using it, but they were licensing it. Apple gave up trying to. Apple and Samsung don't talk to each other, so that will probably never happen, at least not in the near future. HTC tried to license it. I think they failed as well, right? So we'll see. We'll see. But it's very hard to find an OLED tablet. We tried. There's one 7.7 inch. We could not get it working. It was such a pain.
What, the Samsung tablets are not OLED?
Only the 7.7 inch.
Oh, sorry.
The Galaxy Tab all are LCD. Only one Galaxy Tab 7.7 is OLED. We looked high and low.
And why is that?
I have no clue. I need to track someone down in Korea.
Is there something about the cost of larger OLED displays?
Possibly. Supposedly OLED is easier to manufacture. I mean, it can be curved, it can be thin. We see the OLED TVs coming out now. They're like this.
Yeah, no. I'm
wow.
more concerned about yield.
Not clear. But for some reason, even their tablets are not OLED except for one. And we couldn't get it working for the Mobises. My grad student called it up in a fetal position after like 1 week of working with that. He said the code doesn't work. So okay, fine. Let's just do Nexus and S3. So we're working with the Galaxy Nexus and the S3. Fine. When they curl up in fetal positions, you have to help them. You can't do anything after that. Yeah. So we're looking at a whole bunch of power techniques, right, for various devices. So LCD made us happy. Right? And this actually can be applied. So that's why I presented this, and Alec and Sharad said, Victor also said, come talk to your product guys. So, okay. I guess they're busy. I'll try again.
Android, have you released this is it a user level service? Is it a kernel?
Right now we're doing a very naive thing, right? We're actually doing it in the application itself. We haven't even put it as a service or anything like that. We could. We figured the right people to do this are either you guys or Samsung. So I'm also talking to Samsung because this really should be in the kernel or the Android operating system, right? Google, you guys, Samsung are the right people to do this, right? Doing this every application, no app developer wants to do this because it's just going to be more work for them, right? This really shouldn't be an app service. It should be a system service at some level, right? That's the way we looked at it.
So when you say the operating system, do you mean the driver, or where do you mean?
It should be, this is a good question. I know where it is in Linux. And Android to some level, I don't know about Windows. So in Android, for some level, it should go into the kernel bits that actually output to the LCD screen itself. There's a place inside the kernel where there's a video driver, which actually does the last manipulation of the frame buffer to put it into the LCD. That is where you'll do the gamma correction. Right. Yeah. It's the last step in the graphics pipeline, right? Right in the OpenGL pipeline, right before you output to the buffer, you'll do a gamma correction.
That's not done in like firmware or GPU?
It might, but you have to send the right command. I think on some of the newer phones, if you're playing games, it's actually done on the GPU. They're called tessellation lighting, right? TNL. So you want to put in the last TNL step, right? But this will require the graphics experts to figure out where to put it. At some level, all of this, because this is just a brightness compensation, is already there in the pipeline. You have to find the right place and just tweak the settings to use this, and you get it for free. But I don't know where the right place is because every pipeline does it differently, right? Every device does it differently as well at some level. Yeah. So what we are doing now is quite naive. It's actually in the software. I'm using a command line parameter in Linux to change the gamma and brightness, xrandr. For those of you who use Linux, yeah, that's what I'm using to change this now. So system call. Yeah, which is kind of stupid, but it works.
Okay.
Yeah.
Is that it?
That's it. That's all I wanted to say.
Well, thank you very much.
Thank you.